Hello, my name is Ezekiel Dizia. I'm from Program International Electrical Engineering 2023. Uh, uh, my NPM is 2306171846. And now I'm going to presentate about my final projects uh, named Smart Garden Watering System with Soil Moisture and Ambient Temperature Sensors. Next, we have discussions points. The first one is going to be the complexity problems, solution planning, technical method, applications of modern technology, components and device architecture. Next, we have the challenges and complexity of these projects. The challenges are inefficient water usage and lack of adaptability and consistent to environmental changes of traditional watering garden by manually watering yourself. And then next we have the implications of the projects. We have the excessive resource consumptions, meaning excessive usage of water or needing of real-time feedback and automations. Next, we have the solutions planning. Our objectives in these projects are optimizing irrigations using an IoT, meaning sensors and actuators. Uh, the plans are the first one is real-time sensor monitorings, the readings and processings of the sensor data, automating and optimizing based on the processed data, and integrating cloud database logging for further analysis. And next, we have the technical method. The first one is going to be the core concept. The core concept, first of all, is going to be the electronics. So the electronics consists of sensor calibrations and relay operations. Next is the physics. The physics are soil capacitance measurements, water flow control, and water irrigation distributions. Next is the mathematics. The mathematics include the threshold calculations and data analysis. Threshold calculations meaning the threshold on which the ESP32 or the central processing unit will determine what to do, or the decision making of the control processing units. And then we have the constraints. The constraint is going to be a single zone management, meaning that single one ESP32 or one central processing unit is capable of doing one zone of a garden, meaning only one garden, not two garden or many garden. Then we have the limited adaptive capability uh, by using a threshold calculations. The predefined threshold require a manual adjustment for different environment conditions or plant types. Maybe for different garden or different plant type require a predefined threshold that require a manual adjustment of the code. Then we have the dependency of Wi-Fi for data logging and timestamp. Then we have the applications of modern technology in this project. Uh, the modern technology that are used are microcontroller, hardware and software, and the sensors. On the hardware of the microcontroller, we have the ESP32, do it DevKit version 1. Uh, this this have a features dual core processing with Wi-Fi and Bluetooth capabilities. Then it is equipped with a GPIO pin supporting ADC and a digital I/O for sensors and actuator integrations. Next, we have the sensors and module. The sensor we are using are capacitive sensor, soil moisture sensors, the HT22 sensors, water level sensor, and a relay module. Next, we have the software side of this project. The software side has a data logging and visualizations. Then it has a real-time feedback, control logic, Wi-Fi integrations, and NTP synchronizations. This NTP synchronizations is used for getting a timestamp, either for data logging or for time informations. This NTP synchronizations allow us not to use an RTC, so we get the time from web server. Then we have the detailed components and devices. We have the ESP32 itself, act as a central processing units, and it will manage all the input outputs, decision makings and process And it uses a expansions module to accommodate external device that we are going to use. And then we have the sensor itself. We have capacitive sensors. This will sense the capacitance of the soil. This reading of the capacitance is linearly translated to the moisture level, and it uses GPIO 32 until 35, which means we have four capacitive sensors. We have the DHT22. It will monitor environmental conditions. It will prevent plant stresses due to heat or air humidity. It uses GPIO 25 with additional library for data interpretations. And then next we have water level sensors. It will detect water level inside the reservoir. We have a reservoir of water, uh, and it will ensure sufficient supply for the pump. And it uses GPIO 26 of the ESP32. We have a 5-volt relay. It will switch the actuators by the output signal from the ESP32. This uses GPIO 16 and 17. Next, we have the 12-volt water pump. It will activate when the soil is dry or the temperature exceed the threshold. It uses a relay module, and it uses GPIO 16s on the relay module, and it is using the normally open config for the relay. Then we have this 12-volt solenoid. It's a normally closed solenoid. It will open when water inside reservoir is low. This uses the GPIO 17 in tandem with the 5-volt relay. This module configure in normally open configurations for the relay. Then we have the LCD 16 by 2 using an double IC, meaning it will provide real-time feedback and showing critical info. And the additional I2C module is to save the additional wiring into the ESP32. So if for LCD 16 by 2, it needs 8 pin to the ESP32. Now we only need 2 signal pin and 2 power pin, 1 power and 1 ground. Next, we have the components and device documentations. We can see here we have the ESP32 and relay module. This inside the black box, and this is the main module of the project. We have the solenoid itself. The solenoid connected to the the water supply, and then it will connect it to the reservoir. Then we have a water level sensor. This work in tandem with the solenoid. Now we have the pump and the soil moisture sensor. This two also work in tandem. Soil moisture sensors and the pump. The pump will drive the water from the reservoir into the targeted area or targeted garden area. And then we have here the information display LCD, and then we have the power supply. This is the transparent box is the main component of this project. Next, we have the interconnection design. Now we focus on the flow. First of all, the sensor and data flow. The sensor will continuously send analog and digital data to the ESP32, and then the ESP32 process this data to determine the state of the actuator. The actuator control based on the sensor readings and define threshold. The ESP32 send high or low signals to the relay module, triggering the pump and solenoid. Then we have the data display. This data process sensor readings and actuator states are displayed on the LCD for local monitoring. And then the last one, we have the cloud integrations. Cloud integrations will integrate cloud to data log the sensor readings and actuator states for further monitoring or further analysis. And we have here the high-level workflow, the work flow diagram of this project. We have it will start the program. If we turn it on, we will start the program, and then the program will collect the data, and then the data itself will be calculated The capacitive soil moisture sensor will be calculated, will be averaged, and then DHT22 will be interpreted with additional libraries. And then we have threshold and decision making. This is the important part of the project, of the program itself. And then the relay activate actuator based on the logic or based on the decision making that the ESP32 done. And then we have the data displaying and then data logging, and it will loop entirely from the sensor data collections, calculation, decision making, and stuff. And then we have the detailed workflow. The detailed workflow work as also very similarly. We have here the read sensor data. This will read all the sensors. Then we have the control actuators. It will control pump based on moisture level, control solenoid based on moisture level. Then we have the log data to Firebase, and before we log the data, we display the data into the LCD. It will display the moisture level, pump state, and solenoid state, and then it will be displayed for 1 second. So the refresh rate of the LCD is going to be 1 Hz. And then we have here logging data to Firebase. This is the prerequisites of the data logging. This is to make sure that the data that are sent to the Firebase database are true and correct with the respective format. Then we have the utility functions here. Next. This is the whole system documentations here. We have the system photo. This is the main module. This is the clear box here. The main module, it has ESP32 relay power supply below this black box, and then we have the sensors. We have the soil moisture sensor, as you can see here, 1 soil, 1, 2, 3, and 4 soil moisture sensors. We have the DHT22. This is the DHT22, and then we have the water level sensor here on the black tape. And then we have the pump and solenoid as the actuator. We have the solenoid here in the white white box, and then we have the pump. We can see here pump under the reservoir. Then we have the irrigation system. You can see the hoses, all the hoses, the connections, and the water supplies. This hoses is pre-made with a hole, so the water will can flow to water the garden. Next, we have the video of system operations. This is the water level sensor and solenoid. As you can see, it has it just experienced 2 states. The first one, the sensor reads that the water is sufficient, so it will turn off the solenoid, meaning it will close the solenoid, so the water is not flowing. Then, if it's and then the sensor senses that the water is not enough, and it will turn it back on. So it will maintain a very like a 2 centimeters or 3 centimeters of water level. Next, we have the soil moisture sensor and pump working. And I just unplug detach from the soil one of the capacitive moisture sensors, so it will read less moisture, and then it will turn off the pump. I'm plugging it back on, and then it will turn on the pump. You can see here on the state. Yep, it changes from 0 to 1. Pump. This is pump 0 to 1. If it's 1. Why is this 1? Because the the threshold is 2000. You can see here the first reading at 2015, 2155. The pump is off. It's off, and then plug it into the soil. You can see the moisture is 1902, meaning it needs more water, and the pump will turn on. Next, we have a small clip of system operations on reading and data logging. We can see here the moisture sensor reading. This is the moisture sensor readings, and then this is the water level sensor, and then this is the actuator states. The pump is on, solenoid is open. Then we have here, this is done every second, and then we have here done every 30 seconds, which is the data logging to Firebase. We can see here it will prepare the Firebase JSON, and then the JSON data here, the timestamp, moisture, temperature, water level, pump state, and solenoid state. Next, we have the measurement and result. Okay, this is the graph soil moisture versus timestamp. This is the graph illustrate the variations in soil moisture level over time, measured and controlled by smart the garden watering system. We have here the y-axis. Y-axis as the soil moisture represent the analog signal reading from the capacitive soil moisture sensor, and the setup, the higher value indicates a dry soil, the lower value indicates a water soil. And then the x-axis we have the timestamp, represent the time progressions on this is 4th January. Then we have key observations here, fluctuations in soil moisture level. The soil moisture level very dynamically throughout the observations time frame. Short-term increases in soil moisture are evident, likely corresponding to irrigations events. Then we have if we follow each peak, dry soil, and a rapid wet soil is observed, which reflect the soil being watered and rehydrated. We can see the pattern of behavior. After each watering cycle, the soil moisture level stabilizes temporarily before gradually increasing as the soil dries, and then the clinical nature of the graph suggests the consistent monitoring and interventions by the system to maintain an optimal soil moisture range. Then we have the behavioral analysis. The system responsiveness itself, the graph showed that the system effectively responds to soil drying trends by activating the pump before the moisture level drops significantly below the critical threshold that we have set. This ensures the plant roots are not subjective to excessive dryness. And then we have the water usage efficiency. The system only irrigates when necessary, as seen by the sharp transition between dry and wet conditions. This demonstrates the efficiency of the water usage without excessive overwatering. And then the threshold itself, if you are uncomfortable because it's too wet, you can just up the threshold, and vice versa. And then we have the drying trends. The gradual upward trend between irrigations event highlight the natural drying process due to factors such as evaporation, temperature, and plant absorption. Next. And we have another graph, which are the soil moisture, pump, and solenoid states. This graph represents the relationship between soil moisture level, pump state, and solenoid state over time, providing a comprehensive view of the smart watering system operations. We have here the key observation itself. We have soil moisture show periodic fluctuations corresponding to natural drying process and the subsequent watering by system or the interrupt by our systems. The moisture level increases sharply when the pump is activated. And activation occurs when soil moisture fall back below the threshold, ensuring a consistent hydration, meaning it will keep the moisture level at a set point, maybe like for 100 or 200 value of soil moisture. So, and the solenoid operates, we have here the solenoid is on blue, and then the pump is in green. Then we have this, the soil moisture sensor reading. We can see here the soil moisture sensor, the pump state here. We can see maybe here, yeah, you can see the green one from zero because it drops down. Zero, it will go up because it's dropped down. Sorry, here we can see because it's up, it will turn on the pump into one, and then if it's go down to the threshold, to the required threshold, it will turn the pump off. And then we have the solenoid state. It will work after the pump is on, which drains the it will drain the reservoir, and it will go up here. You can see it will occur uh, after the green peak has been up, and then several minutes, and the blue one will go up again. Oh yeah, the left one is the soil moisture level, the right one is the pump state, and the axis is the timestamp like before. We have here we have key observations here. The uh, right one being the, if it's on it's 1, if it's off it's 0. And then the we can see here the recovery. Each pump activations event is followed by a steady decrease in soil moisture level as the water saturates in the soil. When this moisture level fall below predefined threshold, approximately 2000s, the pump turn off or state 0, preventing overwatering. The repetitive pattern. The graph showed a clinical pattern of pump activation and deactivations, reflecting the system ability to maintain soil moisture within desired range at a given time. And the dynamic control, the timing of the pump activation correlates with increased soil dryness, demonstrating that the system is responsive to the real-time conditions, not other natural stuff. And then we have the behavioral analysis. The system responsiveness. The system promptly activates the pump when soil moisture exceeds the dryness threshold 2000 to 2100, preventing the plants from experiencing prolonged dryness. The system quickly deactivates the pump after the soil is adequately rehydrated, ensuring the efficient use of resources. And we have the resources conservations. The pump behavior indicates a minimal water wastage as it deactivates once the soil reaches optimal moisture level. This is the visual comparisons of not using our smart garden system and not using smart garden system. We can see here visually we have cracking of the soil. Then we have here the very moist looking soil. Note though, both photo are same garden, like only divided by a physical barrier, and the both garden are uh, regularly watered, except the smart garden one is not watered by manual. It's not watered manually, but the one they are not using a smart garden is watered uh, is watered regularly. uh, Even on the recording of the data on the smart garden, the not smart garden, the one that is not using smart garden is also being watered. Okay, thank you very much to listen to my final project of Embedded System 1 2024 final project presentations. My name is Isaac Alizia. Thank you for listening.